Welcome back, Physics 30. So we're continuing on here. We did the example dealing with the difference of static and kinetic friction, how the static friction is a bigger number that you have to overcome to get an object moving. Then, of course, once it gets moving, kinetic friction takes over. So for this video, we'll look at the positives and negatives of friction. Friction can be a hindrance. It slows down moving objects and causes heating and binding of parts in machinery. Friction can be reduced by using lubricants such as oil. More effective in reducing friction between two surfaces is to maintain a layer of air or other gas between them, such as air tracks and air tables, in which a layer of air is maintained by forcing air through many tiny holes. Another technique to maintain the air layer is to suspend objects in air using magnetic fields or magnetic levitation. Friction can be helpful. For example, you wouldn't be able to walk if it wasn't for friction, because the soles of your feet touch the ground and there is friction involved there. The movement of a car and also its stability depend upon friction. When friction is low, such as on ice, safe walking or driving becomes difficult. Okay, look at this example, a box against a wall. You can hold a box against a rough wall, see figure below, and prevent it from slipping. So if you're entering your house, you have a big heavy box, you don't want to put it down. So you may realize that, hey, if you kind of hold it up against the wall, you can unlock the door, etc. to come in. So how does that work? Now, if you take a look here, the free body diagram is a little bit different. If we can redraw this a little bit, so here is our surface. We have our box. Our FA is actually going to be this way. Of course, FG is downward. And F normal, the force perpendicular to the surface, is actually here. So you can kind of think of it as equal and opposite to FA in this case. Usually it's FG, right? But if we're pushing something this way and have our surface vertically, we have that. Now, again, the force of friction that we talked about earlier, so we have the coefficient of friction, whichever it is FF over Fn, or rearranging for FF. Of course, it's the coefficient of friction. So that number that represents the two substances pushing against each other, and Fn. So if I can now, again, friction is going to be, this box is going to want to fall down. So friction is actually working against Fg. So it's kind of a different scenario here than we're used to. So I'm going to want to increase this so that it's equal to Fg, or maybe even greater. Now, the force of friction depends upon these two substances, so box and wall. I can't change that, but hey, I can change Fn, and I can change Fn by making Fa bigger. So first of all, this only works if friction is present. And pushing harder on the box, and of course that's Fa, will increase Fn. So these are both action-reaction forces. And we can see horizontally, this box isn't going to move left or right. It's not going to accelerate left or right. So horizontally, our two forces of Fa and Fn must be equal and opposite. And we can put down this. If I increase this, I end up increasing that. And of course, since Fg does not change, more friction results in object not slipping downwards. So it's kind of an interesting scenario here. Our variables are kind of in different spots than what we're used to. But we can see here that friction depends upon normal force. The normal force is the force that's perpendicular to the surface I'm talking about. So this right here, this surface. So if I can increase that by pushing harder on the wall, I'm going to make the normal force larger as well. So that'll prevent it from slipping down. Okay, we'll take a look at another example that we've seen with kind of a tweak. Very similar, we did one like this in a previous section. The only additional part is going to be the addition of friction in this case. So we have a 10 kg box pulled along a horizontal surface, as you see over here, and it's a 40 Newton applied force, and it's applied at 30 degrees above the horizontal. We have the kinetic friction, the mu k value, and we're asked to calculate the acceleration. Of course, there's quite a few things we're going to have to calculate here before we can calculate the acceleration. So if I kind of redraw this free body diagram a little bit, of course I have Fg pulling downwards. I am pulling it this way at an angle. Now this force here is made up of course, oh yes, Fx and Fy. We can break those down into two components. Okay, and we'll also have friction working against us. And lastly, we will have a normal force. Now, the normal force, just like when we did this example before, is not equal and opposite to Fg, because guess what? I have two different forces that are operating upwards. I have this one, Fy, and Fn. And of course, those two should total to be equal and opposite to Fg. So I'm going to have to analyze it vertically, basically figure out all of these forces involved, and then I'll be able to figure out the acceleration. Okay, so things I do know, I can figure out Fg. So Fg is equal to mass times the gravitational acceleration. And it's that old mysterious box that we've dealt with before. So Fg is equal to negative 98 newtons. Okay, so I know what Fg is now. So let's make a little check mark there. I know what that is. Fx and Fy I'm going to have to figure out. So let's figure out Fx next. Of course, Fx is the adjacent side of the hypotenuse. And of course, the applied force, this hypotenuse, is 40 newtons. So yes, cosine is what I'm going to be using. Cos of 30 is equal to adjacent over hype. So Fx is going to be equal to 40 multiplied by cos of 30. Make sure your calculator's in degree mode. And I'll get 34.6 newtons. Okay, so I know what Fx is. Fy, Fyi, we use sine because it is the opposite side of the angle. So sine of 30 is equal to Fy over 40. Okay, I'm kind of running out of room here, so 40 multiplied by sine of 30. And Fy equals 20 newtons. So I know Fy. Fn, I don't know, but I can figure that out next by analyzing the scenario vertically. So over here, let's see, vertically, F net, all my vertical forces include Fn, Fy, and Fg. And since this box isn't accelerating upwards or downwards, I know that my net force vertically is going to be 0. So Fy, I just figured that out, 20. Fg is negative 98. So Fn and 20 minus 98 is negative 78. Add that to each side, and of course Fn works out to be 78 newtons. I can put a positive there. It's upwards. Now, of course, that's going to help me figure out something else here. I can now figure out, so I know Fn, and I can figure out the last thing I need to know, Ff. Because Ff is equal to mu multiplied by the normal force. Now, I was told it was kinetic friction here, so technically it's mu k. Its value is 0.3. .30 multiplied by 78. Don't worry about the signs just yet. My friction force is going to be 23.4 newtons. So that is the friction that's working against me pulling it. So to figure out acceleration, of course acceleration, we need to find out F net. And F net, that refers to the horizontal F net. So analyzing it horizontally. So yeah, this is very similar. We did a question similar to this, except we didn't have the friction come into play. So F net, my horizontal forces include Fx and Ff. And this time I will be accelerating because my Fx force is 34.6. My friction force, be careful here. It's 23.4 newtons, but of course it's working against us. So we have to put in a negative there. Put a little star there. That's a common mistake I usually see. People just simply put this as 23.4. But no, it's working against you. So make sure you have a negative in front. So F net, 34.6 minus 23.4, we get 11.2 newtons. So overall, the net force forward is 11.2 newtons. So we'll plug that into here. And we can solve for A, divide each side by 10. A works out to be 1.1 meters per second squared. And I can put a plus in front of it, or I can just simply say forward. It doesn't really matter, as long as I have a direction. So, fairly big question. It involves figuring out every single force involved, analyzing it vertically, horizontally, and in most cases, we have an acceleration in the horizontal direction, or parallel to the surface. Our next video and last video for this section will look at inclines, in which horizontally we kind of treat as parallel to the surface in which the object is moving. But in this case, we can just simply say horizontal. Okay, we have one more video to go. We'll see you in a bit.